In the end of the 19th century, Heaviside analyzed moving charge by using Maxwell's equation. So Heaviside, he considered a charge moving with uniform motion, speed v, and analyzed the electric field generated by this charge that is in motion. And by using Maxwell's equation, he found that the electric field will increase, the amplitude of the electric field will increase with the speed of motion of the charge. And it goes to infinite when v equals c. So when c is the speed of light. So when the speed of motion equals the speed of light, the amplitude of the field becomes infinite. At that time, there was discussion between Heaviside and Searle also contribute to this analysis. And Searle said that because of that, the charge cannot reach the speed of light because the field will become infinite. But Heaviside said that he is not afraid of infinity, and he did analysis of what will happen if the charge moves faster than the speed of light. And in the same journal, he analyzed this, and he will get some shock waves when v faster than the speed of light. And the angle here is determined by what we call the Mach angle. So the same thing, the same phenomena is that it is observed for in acoustics or for sound waves. So that problem of the moving charge and the electric field becomes infinite. Is it true, or is this maybe not a correct interpretation of the utilization of Maxwell's equation? So in our case, we analyzed a plane electromagnetic wave So we have a plane electromagnetic wave source. This is a source, and wanted to analyze what happened when the source is moving. So we use the FDTD, and we want to see what happened when the source is moving. So before going to that, I want to explain previously what another analysis I did with FDTD that make me think that maybe also in this situation there is a problem. The previous analysis was for the Fabry-Perot cavity. So in Fabry-Perot cavity, imagine you have a plane electromagnetic wave, and you have a partially reflecting surface like this. So some of the wave will be transmitted, and some of the wave will be reflected. So we call this partially reflecting surface. Some wave transmitted, some wave reflected. If you add another one, so I make it simpler like this. If I add another one, what's going to happen? This is a Fabry-Perot cavity. You will have the first transmitted wave will be T, and that's the first one. And then you have reflection here, and you go here. You will have T square. Oh, sorry, the first one will be T square. Because T, so T squared, then you have here T to the power of force, T is still T squared, sorry, but R squared, T R squared, and we have to take into account the phase, 2D. So here this is D, and the next one will be T squared R to the power of force, and here you will have 4D. So this one actually is T squared, the sum from n equal 0 to infinite of R power of n minus gk nd. So this is a sum of a geometrical series. It is T squared over 1 minus R squared exponential, sorry, this one, exponential minus g k, here there is 2d. If so, r and t, they are complex number. If you take the maximum, so the maximum you can have for the maximum of the transmission. So depending on the frequency, K is wave number, so 2πf over c. So depending on the frequency, at the resonance you will have everything transmitted. So at the resonance here you will have the modulus of R square. So the maximum it is T square over 1 minus R square. And if the surface, the reflecting surface is passive and no lossy, we should have T square plus R square equal 1. Okay? So if you do that, you use that here, the maximum will be 1. In general, you will have this kind of response. This is frequency, and this is amplitude, and this is 1. You will have something like this, okay? Depending on the surface you use. So this is first resonance, and then the next resonance. And the maximum amplitude you have is 1. That's maximum transmission you have. No, that's conservation of energy. The maximum of power that will have transmitted on the other side will be 1. That's in the fabricator if you excite from outside. If you excite the fabricator from inside, like this, and you do the same analysis of the transmission, so you have one wave here, one wave here, you will add all of them, you're gonna have something like this: T sum of n equals 0 to infinite, R exponential minus G to, okay, I'm not sure here, 2 or 1, like this, but that's not very important. What is important here? Important here is the maximum will be given by something like this: T minus 1 minus R. Okay? And if we use this formula, which is T equal 1 minus R square root, if we use this, we're gonna find that the maximum is 1 minus R, 1 plus R, 1 minus R. Okay, here that's important because here the maximum is not limited to 1. It's more, it can be more than 1. So how is it possible? How is it possible that you use a plane arithmetic wave and you use the fabricator, you put it inside the fabricator cavity, and the amplitude can be more than 1? The issue here is that this plane wave source is not interacting with the electromagnetic waves. This is like a source with infinite impedance. A source with infinite impedance is basically a bad source. It doesn't radiate, so it needs to have an impedance. If you instead of having this source with no impedance, we add an impedance, we're going to find a different formula for the transmission, and we will find that the energy is conserved. The amplitude will never be more than the 1. The transmitted coefficient will never be more than 1. So that's why I thought that maybe there is a similar issue in what Heaviside was doing. So we still use Maxwell's equation using the FDTD, and we have a plane electric wave. And this plane electric wave source, we're gonna move it with speed v and analyze the electric field generated by this moving the plane electromagnetic wave source. And we found that if we use this kind of source with no resistor, with no impedance, with infinite impedance, the amplitude, yes, it's increased. It increased something like with 1 minus v over c, something like that. The amplitude increase. It doesn't matter really what's its exact formula, but it increases with the speed v and becomes infinite when v equals c. But if we use a source with an impedance, then we found it doesn't increase. So for us, this resolved a 19th century problem that Heaviside had at that time when he used Maxwell's equation. We also use Maxwell's equation that we resolve numerically, and we use a plane electricity wave source in motion, and we found that if this plane electricity wave source has impedance, then we will not observe an increase of the amplitude with the speed.